Welcome. In this video, we're going to go over a classic optimization problem, which is cutting out the corners of a flat piece of cardboard and creating a box by folding up the resulting flaps, folding them upward to create a box of sorts. So here's the piece of cardboard and here's the resulting box. So a box with an open top is to be constructed from a rectangular piece of cardboard whose dimensions are 3 by 5 feet. So let's quickly label that. So this shorter end is 3 feet and this longer end is 5 feet. This will be done by cutting out a square from each of the four corners and bending up the sides. Find the largest volume that such a box can have. So let's begin now that we have these labeled by writing out our objective and our constraint. So our objective is to maximize the volume. And remember, volume for a rectangular solid like this is given by length times width times height. Now, what is our constraint? Well, clearly we're constrained by the size of the flat piece of cardboard. So let's go ahead and label this cardboard so I can come up with, what my length is, what my width, and what my height are. So we don't know how large these corners are going to be yet. I just know I'm going to make these cuts and they're all going to be the same size. So that means all these corners are the same. So I'm labeling them as such. And I'm going to label this X here. So now if this distance here is X, that means this distance here is also X. So what is this distance here? Well, from here to here, this is 3 feet, since this is the shorter side. So I have 3 feet, and I'm subtracting an X, and then I'm subtracting another X. That tells me that this distance here in blue is 3 minus 2x. Now, what about this distance? Well, I'm beginning with 5 feet and I'm subtracting x and I'm subtracting another x. So this is 5 minus 2x. And I'll label this in pink. So now let's relate this to the box, the resulting box. Each of these heights, this is our x here. Now this longer side corresponds, oops, wrong color. This longer side here corresponds to this longer side here. So I'm going to sketch it in pink, and it's 5 minus 2x. And this shorter side here corresponds to this side in blue. So this is 3 minus 2x. So I'm going to label this as my L, my length, this as my width, and x as my height. So height equals x, length equals 5 minus 2x, and width equals 3 minus 2x. Now I can put together a function that represents my volume, and it's a function of x. Each of these are a function of x. So my volume as a function of x, v of x, is equal to the length, which is 5 minus 2x, times the width of 3 minus 2x times the height of x. This can be rewritten as 4x cubed minus 16x squared plus 15x. This third degree polynomial is going to go up and down somewhere, and we want to find the spot where this is a maximum. But no matter what, whether we're finding a max or a minimum, those occur when the tangent line is horizontal. So that tells us that we want to find the first derivative of v and set that equal to 0. So v prime of x, well, that's equal to 12x squared minus 32x plus 15. So where is this equal to 0? So 0 equals 12x squared minus 32x plus 15. And I'm going to quickly add in a note here. So my note is that by setting this equal to 0, the intent is to find all the horizontal tangent lines, and then we'll determine whether they're a maximum or a minimum. To solve for x, let's go ahead and use the quadratic formula. So that is x equals negative 32 plus or minus the square root of negative 32 squared minus 4 times 12 times 15. And this is divided by 2 times 12. Please take a moment, pause your video, and work this out algebraically, then use a calculator to get approximations. Okay, you should have paused your video, and you end up with x equals 8 plus or minus the square root of 19 over 6. So x equals 8 plus root 19 over 6. And x equals 8 minus the square root of 19 divided by 6. Okay, as you can see, I just shifted the screen a little, and that was just to make more space. So what we get for our two values is x is approximately 2.060, and x is approximately 0.607. Now we need to determine which of these is a max and which of these is a min. To determine which is a max and which is a min, you're going to want to use the second derivative test. Okay, so we know what our first derivative is. So v double prime of x, in that case, will be the derivative of this function here. So that's 24x minus 32. Now, what we really need to do, you don't need to come up with a super exact answer here. You just need to determine if the second derivative is larger than 0 or less than 0 at each of these, since remember, if the second derivative, that is, if v double prime is greater than 0, we have a min, and if v double prime is less than 0, we have a max. Okay, so let's go v double prime of about 2, right? And this is fairly close. It's not exact, but it's close. Well, what's that going to be? It's going to be 48 minus 32, that's certainly larger than 0, so there is a min at x equals 2.06. So our maximal value cannot occur here. And in fact, I don't even need to apply the second derivative test again, since I know as this is a third degree polynomial, and by this, I mean our original volume function is a third degree polynomial. As such, I know it's going to behave in this manner. And here, our min, this is going to be at x is about 2.06. So I know that this maximum has to occur at about x equals 0.6. Now, if you want to see that, you can also just approximate, well, what's the second derivative at 6/10, which is 3/5, so at 0.6. That's going to be 24 times 3 over 5 minus 32. Will that be about 60 plus 12, so 72 divided by 5 minus 32. This value is certainly less than 32 since it's going to be, what, like 14 and change? So this is less than 0. So we have a max. So our maximum occurs here. So stop and ask yourself, have we answered our question? We have not. Our original question is to find the largest volume that such a box can have. So we still haven't found that volume, but we can do that now. So our large volume, so we can find this volume by doing length times width times height, and I'm going to use this value here. And let me make a little space. So our height is equal 0.607. Our width is equal to 3 times 2, 3 minus 2 times 0.607. Please get your calculator out and work that out. So that is about 1.786. And now do the same thing here. The length is 5 minus 2 times 0.607. And so that is about 3.786. So our volume, and I want to stress the fact that this is an approximation. Since I did not use the exact value in these calculations, I used an approximation to 3 decimal places. I'm going to round my result to 1 decimal place. So my volume is going to be 3.76 times 1.786, and I missed a digit right here. Look at that. I missed an 8 times 0.607. So go ahead and multiply those 3 values on your own calculator. And we get a volume of about 4.1 feet cubed. So there it is. There is the largest volume such a box can have. And I'll write a nice sentence to complete this problem here. The maximum volume of this box is about 4.1 cubic feet. All right, everybody, keep calm and math on.